So I wanted to talk about the geochemistry of the critical zone this morning, or another way of putting the title was what a critical zonist, and I'm going to define what a critical zonist is, can do with geochemistry. So basically, I'm gonna show you a couple of examples where geochemistry can be useful to understand the critical zone. I have far too much material to show, so I probably will skip over a number of things. And don't feel free to interrupt me if my message is not clear enough. So I wanted to talk about all this, but I probably won't have time. First, I'd like to say a couple of words about the geochemical view of the world. Second, what the geochemists, very short paragraph on what geochemists are able to measure. I will show how we can use geochemistry as a fingerprinting tool. So I'm going to show you an example of what I've called the fingerprinting game. And then, of course, geochemistry is useful for dating. So I will show you some example about dating. And geochemistry can be useful for identifying mechanisms that you don't see. And so this is the smoking gun game, in a way. And then, if I have time, I would like to finish by a couple of examples showing how geochemistry, coupled with other disciplines, can be useful to understand the critical zone as a system. So my definition of the critical zone is pretty simple. This is all what is lying between the rock, bedrock, and weathered bedrock and the lower atmosphere. And I'm looking at it as a system. I mean, at least this is the aim of this Critical Zone Science Initiative, to come back to this study as a system. So let's start with some words about the geochemical view of the world. And I have subtitled that From Galileo to Lovelock. So first, a couple of ideas that I want to make very clear. Geochemistry is not a tool. Even if today I'm going to show you a couple of examples using geochemical tools, geochemistry is not a tool. It's a discipline. It's a science by itself. So it has its main objectives. So the objective of a basic geochemist is to understand the cycle of elements. So when you meet a geochemist in a meeting and you told him, what are you doing right now? And he answers, I'm working on lithium isotopes. Okay, he doesn't say I'm working on the critical zone. He says I'm working on the lithium isotopes. Okay, so and that's respectable. I mean, he has the right to work on lithium isotopes, but he's a geochemist. Okay, so you don't talk to him if you don't want to know more about lithium isotopes. But he can be useful for constraining the behavior of the critical zone. So what is geochemistry? This is a study of the universe and the Earth's history using all the elements from the periodic table, plus the huge number of isotopes that we have. And I will show you a couple of examples where isotopes are very useful. Geochemists have a cyclic vision of the world. They don't have a geological or geographical vision of the world. They have a cyclic vision of the world, meaning that the elements are being cycled all through the Earth's history. This is the main difference when you talk to a geophysicist and a geochemist. Geochemists are probably more cyclic than the geophysics. So if we go into the periodic table, basically all the elements can be useful to study the critical zone. The height of the bars here is simply giving the abundance of the elements. So you see that in green here, we have a number of major elements. And basically, the mass of these major elements represents the mass. Okay? What usually hydrologists or geophysicists or physicists are interested in is a mass. We're not looking at the mass, we're looking at part of the mass. Okay? And when you look at the the red elements here, you have a significant part of the mass. But when you're looking at, for example, this guy, you don't even see his name here, or this guy, which is osmium, it's very rare. So you're absolutely not looking at the mass, you're looking at a tracer, like a spy, which is following a major element most of the time, and so which is giving you indication of the way the major elements behave and then the mass. Okay, so geochemistry is a very indirect science. Okay, you're taking your favorite element because you want to use it as a tracer, as a spy. Okay, so it's giving you indirect indication. It's giving indication about what is happening to the mass, of course, but it's giving information biased by his own behavior. Okay. So at the Earth's surface, you have to know that, because I'm going to use this concept a lot today. This guy, which is Goldschmidt, you have a picture of Goldschmidt here. Vladimir Goldschmidt is one of the fathers of geochemistry. We have two fathers, actually, or we have a father and a mother, if you wish. So he's in the field here with Albert Einstein that you recognize here. So he basically classified the elements on a very simple diagram, which is the ionic radius versus the ionic charge balance. Okay, +2, +3, +4, +5, and this is the ionic radio. And he defined 3 domains. The first domain is here. It's in particular, this is the domain of the alkali elements like sodium, potassium, rubidium, cesium. They are soluble, which means that when they are in contact with water, they're going to migrate into the water phase. Okay? So they're going to be partitioned between the water and the solid. So this is interesting for the critical zone study because we are looking at a porous media. And so we're interested by looking at elements which are going to be partitioned. Okay? And these guys here at the other end of the diagram are also soluble, but they exist in nature in the form of what we call oxyanions, which is a combination of the element with oxygen. You have examples here. Very famous example as sulfur, which exists in nature as sulfate ion, or carbon, which exists in nature as carbonate or bicarbonate ion in nature. In between, you have a domain, which is a gray domain here, where you have insoluble element. This is a very binary vision of the world, but it's enough, okay? It's not good to show that to a chemist because it tells you that chemistry is more complicated than that. But for geochemical purposes, this is basically the information which is enough to know. So the insoluble element in the gray part here of the diagram are insoluble. So you would say, well, they're not interesting for studying the critical zone where water is interacting with solids, but actually they are, because they will be concentrated by weathering processes in the critical zone. So the geochemical view world is made of, is a cyclic vision, as I told you. It's made of, the world of a geochemist is made of reservoirs and fluxes, arrows between these reservoirs. Okay, so I've showed you here a couple of examples of the carbon cycle, which is the most famous one, but of course we have a cycle for all the elements and we have a cycle for all the isotopes. So it keeps us busy for the rest of our lives. And just to make a self-promotion, we recently published a paper with the philosopher Bruno Latour. It just came out last week, so I'm really happy to talk about that, which is trying to change our classical vision of the world, the Earth actually, where you recognize the core, the mantle, the continental crust, and the soil. And actually the critical zone is going to be a very, very thin, almost invisible veneer at the surface of this diagram. And so we invented a new word, a new globe, which is this one, which is a critical zone centered, where the critical zone is here. So you have the atmosphere here, you have the soil here, you have the critical zone here. So this guy here is a porous media in which the elements are going to interact with each other, and what I'm going to talk about later. And of course, in that vision, the mantle is at the periphery. So what was central has become peripheric. In other words, it's not going to make geophysicists happy or mantle geophysicists happy, because of course they're studying something which is very peripheral, but we are studying something which is very central. The advantage of this representation is that this is in the center of this new globe, the sun energy is starting to change the critical zone. I mean, the sun energy is, as you know, is responsible for all the transformation, the chemical and biological transformation which are occurring in the critical zone. And so this new view of the globe is offering a good perspective on how the biogeochemical cycles are being orchestrated by the sun. And finally, just a slide on geochemical history. This guy, which was Vladimir Vernadsky, which is the second father of the geochemist, was a Russian guy, wrote a book in French that you really should write if you're interested. It has been translated in English, not very recently. It has been translated in English. It was written in 1920, and it's called La Biosphère, the biosphere, and basically is explaining what the critical zone is, which is this thin pellicule of the Earth, which has been transformed by the sun energy over geological time. Okay, so this was, you see, I wanted to say a couple of words for the way the geochemist sees the world, and it may explain why maybe often you say, well, it's impossible to talk to geochemists, you know. Okay, but they have their own vision of the world. So what are we able to measure? It's very simple. We are able to measure basically everything. We've been doing a lot progress over the last, let's say, 50 years. You can see that in a lifetime. I mean, in my own lifetime, I can see the way we were measuring concentration when I was a PhD student has nothing to see with the way we are now measuring things in the lab. So we are very precise, and something which is important for you to know, we are much more precise on ratios than we are on concentration. So basically, geochemist doesn't like very much concentrations, because for a concentration, you will be precise at best, like at 2, 3, 5%. But on a ratio, you can be precise as low as 10 to the minus 6. And if you take, for example, isotopic ratio, and this is one of our favorite tracer is strontium isotope, 87 strontium over 86 strontium. In the lab, if you are correct, you can make a measurement with a precision of 10 to the 200 ppm. Okay, so it's really impressive the way geochemists are measuring things very precisely. Okay, so for example, the strontium isotopic ratio of seawater, which is not far from here, is constant because the strontium has a very long residence time in the ocean. It's constant, and we know it. It's 70917, and the 7 is significant. Okay. We are very good in the detection limits also. So probably the world's champion is osmium, which is an element which is which is not very abundant on Earth. Okay, it's worse than gold. Gold is abundant when compared to osmium, and we are able to detect levels of osmium, for example, in a rock or in water sample, as low as 10 to the minus 12 mole per gram, which is very, very low. Very soon we will be able to count the atoms. Okay, remember a mole is the Avogadro number is 10 to the 23, okay? So we're not far. And if you look at the range of concentration of elements in water, so this is a compilation I did a couple of years ago, it varies a lot, okay? It varies a lot between the major elements here. So silica, calcium, magnesium, sodium, sulfur, and potassium are the major elements. Basically, they bring the mass in a sample. And all the others, going down to 10, femtogram per liter. So femto is 10 to the minus 12 gram per liter. So a very large range of variation, which are measurable. Okay, we know how to measure that. Huh? This is my point here today. And of course, the first order variation, control of this concentration in continental water is the bedrock. Huh? You don't have a lot of radium in water just because you don't have a lot of radium in the Earth's crust. And we have a bunch of analytical facilities. I'm not going to spend too much time on that, and I invite you to visit the first geochemical lab that you will meet. This is the golden tool of geochemistry. This is an Icp-Ms. It costs a lot of money. So this is why you have a lot of troubles with your colleagues at the university, because you are expensive, as they say. Of course, you need to work in very clean conditions, because when you're working on these guys here, you have to be cautious not contaminating your sample by your own experiment. So this is why we are using these clean rooms and we are wearing these fancy costumes here. So this is a principle of mass spectrometer. Basically, it's acceleration in an electrical field and then deviation in a magnetic field. This is very classical. I wanted to show you today what is the cutting edge of geochemical analysis with an Icp-Ms. It's laser ablation. In other words, more generally, we're now able to measure in situ things. And I think for porous media science it could be interesting. So more and more, we will be able to measure very small samples in situ. Okay, so we're not dissolving the rock like 1 kilo of basalt that you dissolve in acid and then you measure whatever the osmium or rhenium isotopes. But here we're looking at something which is very, very small sample and that we are able to mineralize using a laser. So using the energy of a laser, you can make the ions very locally and then analyze them. And just to show you what we are able to do, so this is a clast. This is one of my favorite rocks. This is a clast. I'm going to show you this clast a number of times after. So this is an andesite. This is a volcanic bomb which has been partly weathered. It's coming from Guadeloupe. And so this is a core. Okay, this is a bedrock here. This is an andesite. And this is a weathered rind, weathered pellicule. Okay, so this is derived from this by chemical weathering. And now we're able to map. Okay, it's really impressive. Like 20 years ago, it was impossible, almost not, you cannot imagine that you would be able to do that one day. So you can look at the map of the calcium, a map of the manganese, a map of the aluminum, etc. You do see, for example, that aluminum is enriched, okay, in the weathering rind compared to the bedrock. And you know why. This is because of the Goldschmidt diagram that I showed you before. This element is not soluble, so it's getting concentrated into the weathering rinds, okay? But of course, calcium is leaving the rock because calcium is a soluble element, and that's even worse for uranium. Uranium is, no, bad example. Okay, so what are we going to use? Concentration or ratio? We could have spent one hour on that big dispute of concentration, because I know hydrologists do like concentrations, because the concentration is going to be diluted by hydrology in a way. Actually, in geochemistry, we prefer ratios because ratios are more precise. So there is good and bad in the two. Concentration, you can relate the concentration to activities, thermodynamic activities, and then you have thermodynamics behind. You have a theory which goes back to the 18th century, which is based on the first and the second principle of thermodynamics. There are some thermodynamics here. Okay, this is exactly the first and the second principle here. So we have a theory. Okay, so when we work with concentration, we are happy because we have something we can compare with a theory. When we work with ratio, we also have the theory, but it's the main advantage of ratio is that immediately, if you have a ratio doesn't depend upon the volume. So it's an intensive variable, and it doesn't depend on the mass or of the volume. So it has a main advantage. For example, you can write this very straightforward mixing equation where a ratio of a mixture is x plus 1 minus x times the ratio of the two end members. Okay? So let's start with real geochemistry now. I'm going to show you a couple of examples on how to use geochemical tools to fingerprint the critical zone. And so the first example I'd like to take, but I'm absolutely not an expert, and there are people in the room which are much more expert than me. Daniela is a person to be asked if you want to know more about these things. Of course, the most evident thing, if you want to study the movement of water in the critical zone, is to play with the isotopes of water, which is the isotope of oxygen and the isotope of hydrogen. It has been for a very, very long time that there is a relationship between the isotopic composition of hydrogen and the isotopic composition of oxygen in the rainwater. So if you follow the isotopic composition of oxygen and hydrogen in, let's say, a soil water, a groundwater, a river water, you will learn something about the sources of the water. Okay? In theory, this is very simple. In practice, this is much more difficult. And it is a figure that I've taken from a very recent paper from Ocean et al. And there is also the paper in which Daniela is involved, which is the SAVI paper, that they're using oxygen and hydrogen isotopes in a critical zone in the Hill River watershed in California to know where does the water come from. Or in other words, for example, where does the trees take their water from. And it's working very well. You can say, for example, that if the tree has isotopic composition which is in this range, then the tree is taking up the water from the soil moisture reservoir. And if the tree has an isotopic signature which is lying on the meteoritic, what we call the meteoritic line, then it's taking its water from very mobile water. But if you look at these papers actually in details, and Daniela, feel free to interrupt me if you disagree with me, we still do not understand why these waters has the composition they have actually. There is a lot to be understood actually to understand, to know why this kind of water, which is a soil moisture, it's very tightly bound water to the particles and minerals, have the isotopic composition they have, and in particular, why they don't fit on the meteoritic line. So it's simple in principle. It's very complicated, really, to understand what is causing the isotopic composition of water in the critical zone. So much simpler is the use of strontium. So strontium is one of our favorite elements. We are able, as I showed you before, to measure this ratio, 87/86, very precisely. Okay? And the good thing about the strontiums is that they are very heavy. The 87 and the 86, they're very heavy, so the relative mass difference is 1/87, so it's very low. And so when you have a physical, chemical, or biological reaction occurring into the critical zone, they are not discriminated. In other words, in our jargon, we say that they're not fractionated. So no fractionation of isotopes of these two guys here when you, whether chemically or rock, when you take strontium, when a plant is taking up strontium from the soil, or when strontium is migrating by like diffusion in a groundwater. Okay? No isotopic fractionation. So the conclusion is that you can use the 87/86 strontium ratio as a source tracer. Okay? So when you analyze the strontium in a water body, you know where the strontium is coming from, independently of what the different mechanisms and reactions that have made him soluble. Okay? And so most of the variability is due to time and variable rubidium and strontium ratio. I'm going to show you very quickly a couple of examples here. So this is an old study, but it's old, but it's still very good study. We use strontium isotopes to trace the origin of waters in the Congo basin here. So the Congo is the second largest river of the world. And if you analyze the isotopic ratio, strontium isotopic ratio of the different tributaries in the Congo River basin, you end up with this nice geochemical diagram, which is a mixing diagram, actually. Yeah? And here I have put the isotopic composition of the different end members. So these diagrams, I'm not going into the details here, but this diagram is showing that in order to interpret the strontium isotopic ratio of the different waters of the Congo basin, you need to have a mixing between silicate weathering, so silicate weathering providing strontium to the river water, rainwater. Rainwater is a significant input of strontium to the Congo River waters, and this is mainly because they are very dilute. It's a very it's a very wet region of the world, so the rainwater is very high, and the rainwater contribution to strontium is very high as well. And you have carbonates, okay? You need to have a carbonate in member. You need to have strontium coming from carbonates in the Congo. When we showed this picture to geologists, they just said, no, you're wrong. It's impossible. There is no carbonate in the Congo basin. Everybody has been knowing that for centuries. but they're wrong. Yeah?
How does strontium get into rainwater?
Yeah, it's a good question. There are two, mainly the origin is sea salts, okay? So during storms or big tides, you have very small seawater particles, we call that sea salts, which are reaching the atmosphere, and they can travel over very, very long distance. And then it rains, they're getting leached out by the rain, okay? So you find it significantly in the rainwater, and it has a seawater composition. Yeah?
Why are the ratios so constant?
Good point. It will give me if you give me another 1 hour, I can explain that to you. Okay. Okay, basically the crust is high, constant and very different as well.
Yeah,
huh?
I mean, like you say in seawater.
Yeah, so seawater is a very big reservoir at the surface of the Earth.
So you should have fluctuations.
What? No, because the residence time is very high. If you want to change the strontium isotopic ratio of the ocean, you need big impact, like a KT boundary, okay? Otherwise, it doesn't change. Okay, so and it's changing, of course. People are working on the changes of strontium isotopic ratio in the oceans. But if you look at that scale here, on that scale, it doesn't change. Okay, it's buffered in a way. Okay, this is my very simple answer. It's buffered. The carbonate is ancient seawater, so it's very close to the seawater also. But it's very different in that guy here, strontium over sodium ratio. Okay, so we can discriminate the two. And finally, the crust is high because the crust is rubidium rich. And rubidium is radioactive and is decreasing into strontium. And if you have a crust which is old enough, like 2 billion years, then you will have time to build up the strontium isotopic ratio very high. Okay? So of course, if you want to constrain these end members, you need some information, geological information of the basin. Okay? If you do that in the, I don't know, the Vilaine basin, for example, you won't get the same result because the silicated member is not going to be the same. Okay? If you do that in Corsica. Okay, we can play, I'm not going to go into these details here, but you see, this is one information. So the strontium is telling me that I am mixing different water masses. But of course, this information, I can get it from a large number of over ratios. I can work with the calcium-sodium ratio, the magnesium-sodium ratio, the calcium-strontium ratio, blah, blah, blah. So I have a very, very underestimated system, which is something which is classical in geochemistry. We have too much tools, actually. We have too much tracers. So we end up very often in situations where we have too much information. So a mathematical technique which is very useful in geochemistry is the inversion technique, because you have a couple of equations, but you have too much information to fit these equations, and the inversion technique is a very well-adapted one. Because this is a critical zone session, I wanted to show you a couple of strontium isotopic ratio in the critical zone observatory of Lorgeval in the Paris basin in the north of France. So this is a recent study that is going to be published in Hydrological Processes. So this is a catchment. This is a sedimentary basin, and the nice thing about this sedimentary basin is that you have an aquifer which is hosted by a lacustrine limestone and an aquifer which is hosted by a marine limestone. And they have very different isotopic ratio for strontium. And if you look at the strontium isotopes here analyzed in the rocks, you have relatively high strontium isotopic ratio here in the lacustrine formation, and you have very low isotopic ratio in the marine formation. So you can use strontium isotope to trace the origin of the water in the river. Okay, and this is a complicated diagram. Don't pay attention to it, but just to show you that if you look at the isotopic composition of the river here, okay, in Avenel, which is the outlet of the basin, you cannot explain it by the main contributor. I mean, if you look at hydrological models, they all tell you that the main body of water is the aquifer here in the lacustrine limestone. And if you look at the isotopic composition of the strontium, which is here, just look at this high axis here. You see that the Avenel, in particular during the dry season, is lower than the isotopic composition of the lacustrine limestone. So it's impossible that the strontium can come from this aquifer, and you need a second source of strontium. And we propose in that paper that the second source of strontium is due to the dissolution of gypsum, which is present in disseminated lenses here at the base of the marine aquifer. Okay? And the marine aquifer can also contribute. So it's just an example to show you that using strontium isotopes, you can learn a lot about the pathway of waters. And I'm very surprised that in the critical zone studies, strontium isotopes are very, very poorly used, actually. Of course, what you can do with the strontium isotopes, you can also do with the more heavy isotopes. And you can have in the literature a lot of papers that have been using lead isotopes, neodymium isotopes, which are heavy isotopes as well, not fractionated by processes. And I'm not going don't have time to go into that, but there are very, very beautiful studies, a little bit old now, but if you're interested, you can look at that paper from Tom Bullen and Carol Kendall in this famous book, Isotope Tracers in Catchment Hydrology. They use the strontium isotopes, and you also use the lead isotopes in nested catchments. And this is a catchment which is the smallest, and this is a catchment which is the largest. Okay, it's a Slippers rivers in the US. So the first catchment is here, the second is here, and the third is here. And when you increase the size of the catchment, you lower the isotopic composition of the strontium, because the residence time, this is the interpretation of the paper, the residence time of the water is getting higher and higher, and so you have time to weather minerals in the rock, in the granite, which have different isotopic ratios. Okay, so it's another way of using the strontium isotopes here. It's not tracing the water masses, it's telling what are the minerals which are being dissolved. Okay? And of course, it depends upon time, so it's a matter of residence time. So actually here, the strontium isotopic ratio in the water is an indicator of the residence time of the water. So very, very powerful. Of course, you need to know the different isotopic composition of the different minerals in the bedrock. Huh? But very, very different. Interesting. Okay, it can be used also, this strontium isotopic ratio, to trace the sediments. So this is, I'm going to skip that. This is tracing the origin of the sediments in large rivers. For example, neodymium isotopes and strontium isotopes in the suspended sediment on the Amazon here. The Amazon, this is the Amazon basin. If you look at the sediments here, the isotopic composition of neodymium and strontium tells you something which is very clear, which is all the sediments of the Amazon here at mouth are derived from a very, very thin region, which is here. So it's indicating you where the physical erosion is occurring. Okay, I'm skipping that. So some ideas to conclude this part of the fingerprinting. Strontium isotopes, but also uranium, lead, neodymium isotopes in water and solids are powerful water tracers and indirect tracers of residence time, okay? Because of the kinetics and the time elapsed, the contact time of the water and the minerals makes you a big difference. It is very surprising that they have not been applied systematically in critical zone observatories. This is very easy to measure, and that's a very good way of quantifying the mixings. The first order result that came out of all these studies using strontium isotopes or radiogenic isotopes as passive tracers is that the first control is mineralogy or lithology, or in other words, the geology, the nature of the minerals, of the materials. Okay, and I just said a couple of words on that, but geochemical systems, when you're using a lot of tracers, are overestimated. So the inversion technique, inversion methods are very useful in geochemistry. Oh, I'm sorry.
From your example in the Congo, you mentioned that you showed this to geologists and they said there's no carbonate.
Yeah.
And we never heard the resolution.
Okay, you're right. I got the question. Yeah, they said, no, it's impossible. We don't have carbonate in the basin. Okay, and if you do geological map, if you look at the geological map, if you try to find one, of course, there is no carbonate. But in the Congo, as you may know, there is 100 meters of laterite. So the bedrock is at the base of the laterite. So, and actually, the carbonate rocks have been found using satellite images. You do see karstic features. You see, you know, valley without rivers, dolins, sinkholes, this kind of. So carbonate do exist. So geochemists have learned how to find carbonates to geologists. Okay. Yeah. So, of course, and this is the origin of geochemistry, we can use isotopes to date. And I'm going to show you a couple of examples, but of course we could spend the whole afternoon on that. Huh? So, radioactivity, you know that, it's one of the most marvelous mathematical laws that have ever been found. It's very simple. It's a negative exponential. So what are we using in the critical zone? So if we want to date processes in the critical zone, we need not short, but short-lived isotopes. Okay? And this is possible in two situations. The first situation is when you have what we call cosmogenic isotopes. A cosmogenic isotope, COSMO, are continuously produced by the bombardment of cosmic rays on Earth. Okay? So there is a process which is constantly producing them. Okay? Otherwise, they will disappear because they have, this is something I didn't say, but we are interested by having isotopes with how do you call that? Half-life, which is short, okay? Half-life of 1 billion years doesn't interest us in the critical zone because, you know, our processes, the processes we are looking at are very short, so we need half-lives very short, okay? And so we need processes which are constantly producing these isotopes, otherwise they would have died. And this is possible when the cosmic ray is bombarding either the atmosphere or the rocks. So this is a difference between what we call the meteoritic cosmogenic isotopes or the in situ cosmogenic isotopes. And there is another bunch of isotopes which is very useful, which is uranium series. I'm going to show you what it is. So which isotopes are useful? So the critical zone. So this is a gallery of isotopes that can be used for studying critical zone processes. The most famous are beryllium-10, carbon-14, aluminum-26, chlorine, 36. Okay, so they're very difficult to measure because they're very, very rare, and so you need a big machine. It's not a machine which is costing 1 million of euros. It's a machine that is costing 20 millions of euros. Okay, we have a couple of this machine in France. The one is not far from here in Marseille, on the other side of the Mediterranean Sea. Okay, so basically the principle is as follows. Cosmic rays are bombarding either the atmosphere or the ground, and they are producing cosmogenic isotopes. So these isotopes are accumulating. So the more exposure time you have, the more of these isotopes here you will get. It's very simple. There is a very interesting technique that has been developed in the last decade by people in particular in Germany at Gaillardet, by my colleague Friedhelm von Blankenburg, and other people in the US as well has worked on that technique, which is using the beryllium-9 and the beryllium-10. The beryllium-9 is derived from the rock, so it's a non-cosmogenic isotope. It's in the rock, just this is a major isotope of beryllium in nature. So when a rock is weathered, it is producing beryllium-9, and this beryllium-9 is found in the soil where it is. It's here, beryllium-9 here. So you do see the primary beryllium-9, so the beryllium-9 from the rock, and then the beryllium-9 gets leached because beryllium is soluble. It's an alkali earth element. Here you have the sorbed beryllium, so the beryllium is being sorbed on the clay minerals in the soil. So you have this factor to take into account, and then the beryllium-10 is produced in the atmosphere. It's a cosmogenic isotope. So of course you find more beryllium-10 at the soil surface than you find in depth, just because you're closer to the production source. And playing with the beryllium-10 and beryllium-9, I'm not going into the details here, it's a very, very elegant, very elegant from a mathematical point of view, and you can show that the very simple ratio, beryllium-10 over beryllium-9, is related to the flux of beryllium-10, which is coming from the atmosphere. So you have to know it, but people have been studying that for decades. So we know it pretty well all over the world. If you measure the beryllium-10 in the parent bedrock, which is easy to do, you take a granite, you take a basalt, and then you measure the beryllium-10 in your lab, and then you can calculate D, which is the denudation, okay, or the uplift rate if you are at steady state. So a very powerful tool, which has not been very, very used so far because it's quite new, but very, very promising. The uranium series is another source of very short-lived isotopes. So very simple. You know that it has been discovered like 1 century ago. Uranium is decaying. So this is, for example, uranium-238 is decaying into lead-206. Okay, but it's not a straightforward reaction. There are a lot of in between. There are a lot of nuclides which are being produced. In particular, you produce thorium-234 here, which again decays into uranium-234. Okay. But the important thing about using these isotopes for studying critical zone processes is that the uranium and the thorium has very, very different behavior. Thorium is insoluble, so it's going to be retained into the solid phase, while uranium is very mobile. Okay, it's an oxyanion. Okay, and it's very mobile. So when you have a weathering, chemical weathering occurring here, for example, at the base of the critical zone, the uranium and the thorium will be separated, okay? And then by looking at measuring the isotope of uranium, you can calculate, I'm not going into the details here, but you can calculate the time elapsed since this fractionation occurred, okay? So you take a sample in the soil profile, you measure the isotopic composition of the uranium, and you can have information about the time that have elapsed since the first incipient chemical weathering occurred. Very powerful. Okay? And you can find a number of studies on that in the literature. I have put a couple of them here. François Chabot in Strasbourg has been working a lot on that technique. Lin Ma from Texas, El Paso has been working a lot also. Bernard Bourdon, Anthony Dossetto, and others. So basically, you can find in that book chapter here the theory which is behind. So uranium is released here by chemical weathering. It's leaving the system by physical erosion. You can write a number of equations. Of course, uranium is leached, so you have a kinetic factor here, but you also have radioactivity because this uranium is radioactive, so it's decaying, and this is why we are using it. We apply that to the... oh, really? Oh, my God. Okay, we apply that to the Amazon basin, and we showed in the Amazon basin that the time, this time that I'm talking about, in the sediments, in the suspended sediments, is very variable depending where you are in the Amazon. So, for example, here at mouth, almost at mouth, the residence time, in a way, of the suspended sediment in the system is 32,000 years. Okay, so it gives you indications of the time of fractionation time. Okay, so I need to go a little bit farther. So I'm concluding this chapter. So PT is allowing us to date surface, transit times, fractionation time between two elements. Of course, we're dealing with open systems. It's very complicated in details. Okay, there are many exchanges between the surface and the solution, surfaces and the solution. So the problem is complicated. Uranium series have a very strong potential, and I think we're just at the beginning of using them, coupled with cosmogenic isotopes. Okay, so maybe I should skip that, which is a pity because okay, so I'm just giving you the idea. So the rationale of this Sherlock Holmes work is to say that we have a couple of isotopes which when they're measured in the water, they tell us something about the processes that have been occurring, okay? And in particular, what we like is to look at the isotopes of trace element, okay? Because a trace element is not entering into the stoichiometry. It's really the perfect spy, okay? So we have spies, we have isotopes of the spies. We're not interested by major elements, because major elements are addressing minor problems, which is one of the famous sentences of geochemistry. And if you want to learn more about these isotopes that we have been using over the past 10 or 20 years, it's very recent, the development of the non-traditional stable isotope geochemistry. You can look at that book, which was published and re-edited in 2017. Okay? So we are looking at the isotopes of, for example, lithium isotopes. And just let me show you what lithium isotopes are telling us. If you look at the lithium isotopes here in the river waters of the Amazon, so this is the Amazon basin. It's divided into big sub-basin here, and we have measured the lithium isotopic composition in the different rivers and sub-basin here. Everything has been published in these papers here. And it's very simple, very simple. If you look at, even at the Amazon, at the scale of the Amazon basin, this is the isotopic composition. So you need to correct from the isotopic composition of the rock, because depending upon the type of rock that you are weathering, the lithium isotopic composition is not going to be the same, but we know how to do that. So this is the isotopic composition of the water, okay? So the Amazon, for example, let's say, is here, okay? This point here is the Amazon. And this is a fraction of lithium which is left in solution, what it is. When a rock is weathering, all the lithium, which is a very soluble element, is getting into the solution. But then, because the lithium has a great affinity for secondary phases, clays, oxides, and all these minerals which are forming into the critical zone just after the dissolution, the lithium is getting reincorporated into the secondary phase. And then there is a big fractionation, discrimination between the 6 lithium and the 7 lithium. So my smoking gun is here. If lithium is being reincorporated into a clay, then the isotopic composition of the water is going to be different. And I can do very simple mathematical models explaining these trends here. I'm not going to the details to explain how we calculate the fraction of lithium which is remaining in solution, or in other words, the fraction of lithium which has been reincorporated into the sediments, but we can calculate it based on sodium, for example, and we end up with very simple relationship. We know the isotopic fractionation, we know the ratio, okay, between the 7 lithium and the 6 lithium when the lithium is getting reincorporated into the clay minerals, because we've been doing experimental work to constrain that. And so we are able to say, okay, the isotopic composition, for example, of the rivers from the lowlands, the lowlands here, okay, this is the lowlands, this is the famous Rio Negro river here, is here, very close to the bedrock, because there is almost no lithium which has been reincorporated into the clay. Okay? But in the floodplain here of the Amazon, this is exactly the reverse situation. Because of the floodplain environment, a lot of lithium has been able to be reincorporated into secondary minerals, and then it has fractionated a lot the isotopic composition. So the water, the isotopic composition of the water is telling me that lithium reincorporation into the clay has been occurring. Okay? So I'm learning something very powerful on the porous media, actually, of the Amazon critical zone. Okay. And then when it's getting interesting, very interesting, is that we can relate, actually, this isotopic composition of the lithium isotope in a river water as a function of weathering intensity. Well, what is it, weathering intensity? Just let me show a diagram, and then I will be okay. Huh? But if I don't show you that, you won't understand anything. So it's a very simple view of the critical zone. It's I don't know if it's a geochemical view or. Imagine the critical zone is created here at the bottom. It's destroyed at the top here. So E is the erosion, physical erosion. It's a flux, okay? It's the amount of mass per unit of time. And D is the total, okay? So it's E plus W. So W is the flux of material which is going to be dissolved. So it's leaving the critical zone. And E is the physical erosion, okay? And so, of course, at steady state, D, denudation, is equals to the sum of E plus W. Okay? And when we look at lithium isotopes in the Amazon River, we have this nice relationship that I'm going to finish on between isotopic composition of lithium in the Amazon rivers as a function of the W over D ratio. How do we know it? But we know it because W can be calculated based on the river chemistry. Okay, I'm counting the sodium, the calcium, the magnesium, and the potassium maybe. I forgot it, which is the total mass dissolved. Okay, and the D is given, for example, by cosmogenic isotopes like beryllium-10 studies. And so this is a very nice relationship. We call it the croissant relationship between the lithium isotopes and the W over D ratio. So it's one of the first evidences where geochemistry in the critical zone, fancy isotopes in the critical zone, are saying something useful for understanding the behavior of the critical zone. Okay, so I think I need to finish. And so my conclusion is going to be, so I had a couple of examples, very interesting, to show you, but oh no, this guy, I think this guy may interesting you. There is a paper which is just coming out, which is really interesting, which is using isotope to trace a purely physical reaction. These colleagues here, Junta et al., measured the chloride and the bromide isotope in a very stagnant aquifer. It's the Illinois aquifer here. And they are interpreting the isotopic fractionation of chloride and bromide as a function of depth in the aquifer by an equilibrium between gravity and diffusion. Gravity because the isotope, the heavy isotope, is going to be more attracted by the Earth, but diffusion because it's a competing process. Okay? So interesting. Okay? Isotopes can be fractionated by this equilibrium between diffusion and gravity. And then I'm concluding. Let me conclude, please. Yeah, of course, a big application of the link between geochemistry and critical zone science is reactive transport. And Jenny is going to talk about that later. And this is my conclusion. So geochemistry puts strong constraints on the formation and evolution of the critical zone. Studies linking geochemical information with other types of informations, hydrological, meteorological, geophysical, biological, are too rare. Okay, so we really need to talk to each other. I mean, the people that develop fancy tools, complicated tools in their labs, and the people which are interested by understanding the behavior of the critical zone as a system to come up with new ideas and new models. Okay, and this is why it's really important to work for networking and share a common language, at least a common language. And I have a great news to announce here is that yesterday, or 2 days before, we were awarded, I mean we, the European, were awarded a European infrastructure called ELTER, which is putting together the critical zone observatories in Europe and the LTER and LTSER. Please come and find me to know what does it mean after, together in a new European research infrastructure. That's going to be a lot of fun. Thank you.